folks, and welcome to a nice new week. Yeah, please, we have a file now as an attendance sheet. Yeah. So, back to Math Eco. Everybody remembers the ideas of closed sets and open sets? What's an open set? What's an open set? So, we don't need that definition, that you can make a smaller definition. What he says is broadly right, but not really accurate. You can make a smaller definition. What that definition be? What's an open set? A set, all of whose points are interior points, is an open set. Okay? And we did something on intersection and unions of open sets, etc. Then we learned about closed sets. What's a closed set? The complement of an open set. Okay? A closed set is a complement of an open set. Alright? Oh. We also learned about limit points. Right? So if you have a sequence x1, x2, xn, how do you define, when do you call x star a point of accumulation or a limit point of that sequence?
Any neighborhood around that point contains one element of the
Sequence apart from x star itself. Every open ball around x star will contain at least one point of the sequence apart from x star itself. Right? All such points are said to be limit points of the set. Okay. Now I'm going to do an important theorem for you. But before that, we can have nice ideas about open sets. Right? Okay, for example, how to define a function? How do you define a function? What's a function? So what's a function from, say, x to y? We have talked about that in the microeconometrics class. What's a function from x to y? A rule which assigns for every element of the set x a unique element of the set y. Right? Every element of the set x a unique element of the set y. Right? So now if you take y and if you take x and if you define a function f of x, right? Okay? So for example, what does that function do? That function takes the point, say f of x is equal to y is equal to 2 plus 3x. So what does that function do? It takes the value x, and what value does it make of x? If x equal to 1, what value does the function make of x? 5. So it takes the point 1 and associates it with the point 5 here. Right? What does it do to the value 2? 8. Right? So it takes the value 2, associate the value 0.8. Right? Okay? You know that if you join all these dots, you get a function. Right? So now, let me think of an important idea. Suppose you have got some function like this, f of x. It is very important to distinguish between functions which are continuous and functions which are not continuous. It's very important to distinguish between functions which are continuous and functions which are not continuous. And this is where the ideas of open sets become important. That's one of the applications that we will have of open sets, right? Okay. Now, how do you define continuity? When do you say that a function is a continuous function? Have you heard of this definition before? Continuous functions, not continuous functions. Anybody who's done some math somewhere, yeah?
Function is continuous when it is differentiable at any order.
What does that mean technically?
There are no breaks for.
So what he says is there are no breaks. We need to make that a little bit more rigorous kind of a definition. There are no breaks, right? There are no breaks in the function. Okay? So for example, if you have this as a function, this is a function which is discontinuous. There is a break. Right? Okay? How do you, so we need to now define these definitions, make these ideas formal. How would you do that?
So, sir, a function which is differentiable at all points.
Yeah, but what do you mean by differentiable?
At any point in the function, you can find its derivative.
Yeah, but what do you mean by derivative?
You can find the slope of
Okay, let's try to formalize these ideas a little bit, right? Everybody keeps on saying many things, right? Okay, let's formalize these ideas. We say that a function is continuous. Don't write this down. Just understand. We say that a function is continuous at say some point 2, right? Or in general some point x star. If you think of a sequence of points on x such that, so think of a sequence x1, x2, xn such that the limit of the sequence as n becomes larger is say x star, right? X star. Sure? So think of the x-axis, think of a sequence x1, x2, x3, x4, x5, so on, and think of the limit of the sequence which is x star. So what do you mean by x star? At x star there is necessarily an open interval around, at least one open interval around x star, such that some elements of the sequence are always there in that open interval. Right? Okay. Now, think of the sequence f of x1, f of x2, f of xn. Think of the sequence f of x1, f of x2, f of xn. For each x1 there is an f of x1, each x2 there is an f of x2, x3 there is an f of x3. So think of the sequence f of x1, x2, xn, and think of the limit of this sequence. Right? So think of the limit of f of xn as n tends to, as n becomes larger and larger and larger. Yeah? Right? Now, the function, this function is said to be continuous if limit f of xn is the limit of f of x is equal to f of x star. Can you explain this to me? Explain this idea to me. Yeah.
So as x tends to xn, so x1, x2, as it goes nearer
X tends to x star.
X star, sorry.
Yeah.
So the images of each xi will go towards f star, f of x star.
X star. Yeah, perfect. So as x gets closer and closer to x star, f of x should get closer and closer to f of x star. Then the function will be said to be continuous at f of x star. The function is said to be continuous at at x star. Right? Okay? Sure? I can make it more systematic. I can say that whenever, for every x you're getting closer and closer to x star, there exists also an open neighborhood around f of x star which contains f of x. Right? So that sequence idea can really be used there. Right? But effectively what this means is, if x tends to x star, f of x should tend to f of x star. Then the function is said to be continuous at x star. Then the function is said to be continuous at x star. But a function which is continuous at x star need not be continuous at all points. Therefore, we say that the function is continuous if it is continuous at all points. Right? So that's an important thing. For example, here if I do this function, in a sense there is no break in that function, right? Yeah? But is this function a continuous function? So this function goes like this. Does this idea apply to this function? Is this function continuous at, say, if I call this x star? Is this function continuous at x star? No? Why? So think of this. See, for some neighborhood around x star, there exists a neighborhood around x star such that whenever x gets closer and closer to x star, f of x doesn't get closer and closer to f of x star from this side. From this side it does, but from this side it doesn't. You see, as x gets closer and closer to x star, right? Does f of x get closer and closer to f of x star? If x is approaching x star from this side? No. Right? Whereas from this side it works. So this function is said to be left continuous but not right continuous. Yeah. See, as you approach x star from this side, from the left, as x tends to x star, f of x is getting closer and closer to f of x star. But as you approach this from this side, f of x, are you getting closer and closer to f of x star? You aren't, above, no? So therefore this function is continuous from the left but not continuous from here. Right? Okay? Fine? So function, if a function has to be continuous at x star, it has to be continuous both from the right and the left. It has to be right continuous and left continuous. Okay? That is what is meant by a continuous function. Okay? Right. Now, I'll introduce to you an important idea which is going to be very, very important for us. Okay? The ideas of convex sets, separating hyperplanes, supporting hyperplanes, and the theorem about closed sets. All these are going to be very important ideas for us in economics. Right? Okay, so I will now talk about those ideas. So we say, okay, before that let me just talk to you a little bit more about functions. Suppose you have, suppose you have capital here and labor here. You use capital labor in order to produce output. Yeah? So for example, if you use this much amount of capital and this much amount of labor, right, say L1 amount of labor, K1 amount of capital, you can produce, say, Y1 amount of output. Right? If you use, say, L2 amount of labor, K2 amount of capital, you can actually produce Y2 amount of output. So on and so forth. Right? Now, what we are really doing is associating with every pair L and K a real number Y. A unique real number Y, right? Associating with every pair L and K, a real unique number Y. So what we are really doing is we are defining a function from the two-dimensional real space to the one-dimensional real number line, right? So, but what is that? That's a production function, right? That's the production function. So what we are really defining here is a function Lk is what? It's a function from the two-dimensional real space. I say R++ because we are allowing all inputs of labor and capital to be strictly positive. Right? Because you need labor and capital both. Right? From the two-dimensional real space to the real one-dimensional real space, R1. Right? So what you really have is a function from R2 to R1. If you use more inputs, what do you have? The production function becomes a function from a larger space to R1. Similarly, what's the utility function? It's a function from Rk plus to R1. Right? So utility functions, production functions are actually functions of this kind. In general, they are functions from a larger dimensional real space to the real number line. Is this clear to everybody? Okay, and the same idea works for functions. But obviously, you know, when you have say a two-dimensional space or a larger space, then you can't think of continuity in the way we drew it there. It will become a more complex object. Right, so for example, here what we have to say is, for every open set here, right, so what we have to say is, if you think of an open ball here, how will you think of continuity in this case? How will you think of continuity in a function which is R2 to R1? Can you generalize the definition? There effectively what did we say was, if this is x star and if this is a function, we said as x gets closer and closer to x star, f of x should also get closer and closer to f of x star. Right? So whenever x is within some epsilon neighborhood of x star, there must also exist some corresponding neighborhood, say some delta neighborhood around f of x star, such that f of x belongs to that neighborhood. That is the idea of continuity that we are really using. Is this clear? So what we are really saying is, as x gets closer and closer to x star, that is, for every epsilon neighborhood around x star, there must also exist some neighborhood around f of x star, so that f of x belongs to that neighborhood. Right? Now, tell me how you would think of a function from R2 to R1, because with R2 to R1 you can't say a function without a break and all that kind of a thing, because you can't even draw those functions properly. Right? So R2 to R1 kya hoga? How will you define the continuity of a function? Or can I think of more general functions? For example, I can think of a production process which uses 3 inputs to produce 2 outputs. I can think of a farm, for example, which uses manure, which uses seeds, which uses water, which uses labor, which uses machinery to produce 2 crops. Right? Then what would that function be? That function would be from R5 to R2. That production function will be a function from R5 to R2. Right? You need to think of that production function as a continuous function. How will you think of that? That's where the ideas, the more abstract ideas that we have talked about. Right? It says that whenever a function will be continuous at a point x star if, whenever there exists an open neighborhood around, open ball around x star, which contains x, there must exist an open neighborhood around f of x star, right, which contains f of x. So for example, the function from a 3-dimensional space to a 2-dimensional space, then we have a 3-dimensional space, we will get a sphere. So whenever x belongs to that sphere, there must exist an open circle around f of x, x star, which contains f of x. You see, so that's what allows us to think more generally of production of functions. Because the kind of function that we generally understand are not one-dimensional functions in R1 and R2, right? They will be more general functions. Right? For example, think of a production process. Then you have many inputs and many outputs. Then obviously it's a function from a larger R space with a greater dimension than 2 to another R space with a dimension greater than 2. And you need to think of whether production functions are continuous. Why should you think of production functions being continuous? Somebody said you can differentiate it at each point. But what does the derivative of production function tell you? So if I differentiate a production function, marginal products, right? So I need to know whether the marginal products at each point of time. Right, so therefore it's important for me to conceptualize continuity. So how will you conceptualize continuity from R3 to R2? Think of the grandmother treatment. Just think of explaining this to a grandmother properly. How will you do that? Yeah? Take a shot, no problem. Yeah.
You can just from R2 to R1.
No, R2 to R1 go, yes.
On one hand, there will be a curve which will pass through x star and a straight line will go.
In R2 to R1, the idea is quite simple. R2 to R1, it says that for whenever x belongs to the circle, open circle around x star, that is, whenever x belongs to a radius of some epsilon around x star, f of x must belong to some interval around f of x star. F of x must belong to some interval around f of x star. Right, because f of x star will be on R1. X star will be in the two-dimensional. Right, so by open neighborhood around x star in R2 will mean an open circle. So when we say whenever x belongs to an open circle around x star, f of x must belong to an open interval around f of x star. Right, that is from R2 to R1. How will you think of an R3 to R2? Yeah.
When x belongs to a sphere,
Open sphere.
Around
X star.
then there is a function fx which belongs to an open sphere again.
Open circle. Around in two-dimensional space, it's an open circle, no? In a three-dimensional space, it's the open sphere.
Your open circle
Yeah.
f of x belongs to an open circle around fx star.
Yeah. So there exists an open circle around f of x star, which contains f of x. Right? So whenever, that's the way of conceptualizing that when x gets closer to x star in any dimension, f of x gets closer to f of x star in any dimension. Right? Is this clear? That's how you think of continuity in general, because the kind of production functions or utility functions that we are going to, in particular production functions we are going to think about are going to be functions which are functions from, which are going to be multi-input, multi-output functions. No? In a very simple case, we use capital labor to produce output. But in general, we use many inputs to produce many outputs. Yeah, for example, in this classroom, we are using many inputs, the university is using many inputs, labor, the capital, electricity, consumables, etc. to produce many outputs among students. Right? So the production function here is a multi-dimensional production function that way. Right? What's happening in this class is actually a production process where there are inputs and there are outputs. Right? Sure? Is this clear? So therefore, you need to understand. So if you want to, for example, find out the marginal product of a fan, then you need it to be continuous. The production function needs to be continuous at all points. So you need to conceptualize continuity. Yeah? See, in R3, so basic idea is when x gets closer and closer to x star, f of x must get closer and closer to f of x star. Okay. When do you say x gets closer and closer to x star in R3? When for every x, right, there exists an open sphere such that x belongs to that open sphere around f of x star of whatever radius epsilon. Right? Right? Okay. So whenever there exists an open sphere around x star, so that but an open sphere on X star is a set. So whenever X belongs to that set defined by the open sphere, there must also exist an open circle around X star in the two-dimensional space. Right, so it will go like this. Suppose we are using, okay, say labor, capital, and say some other input, okay, say energy. Right. So each point will be a three-dimensional point. It will have an x-axis, a y-axis, and a z-axis, and a set of points around this point, such as the radius of say which set of points which are at a distance say alpha or epsilon from this point will become a three-dimensional sphere. But you are looking at points which are less than epsilon, so this will become an open dimensional sphere without any boundaries on top. Right? Without any boundaries on top. Right? Okay, that will be the set of, so when you consider a set of points which are so close to x, you must think of points which lie at some epsilon distance at x, right? So now this output is going to be converted into say two products, say jawar and sugarcane. So this farmer uses jawar and sugarcane, right? Or uses say sugarcane and say soybean sowed as a crop between sugarcane, right? Okay, so he does that, right? So you have so it will then be somewhere